Tainá,
Já fez a reunião?
Hey, Ashen, you hear me? My voice is clearly. Hello everyone. The meetup starting in few minutes. Good morning. What's your name? Japanese name, Pedro. Pedro, are you Elixir programmer too? Hello, Kevin. Have a nice day today. really like it. Very fast. Elixir in my machine is very slow sometimes. That is written with the Husky language. Meetup starts in 1 minute. Okay. Are you prepared, Marcos? Hello
Hello.
everyone, I'm starting Meetup. Your guests today are Marcos Trindade, Paulo Valente, and myself, Matheus Camargo Marques. This is initiative that aims to reach around 90,000 people
Hello.
by the end of the year. I love in working with Elixir, and I believe everyone here does too. Paulo Valente and myself, Matheus Camargo Marques. This is initiative that aims to reach around 90,000 people
Hello.
by the end of the year. I love in working with Elixir, and I believe everyone here does too. Idea Marx, can you start your presentation?
Sure. Just making the screen bigger. Uh, where is everything? Where am I? Screen. I will just share everything. Let me know if you can see the screen.
I see yours. I can see
I
your
think I'm.
screen.
Okay. So I'm gonna start then. Uh, so morning, good evening, everyone. So my name is Marcos. So I'm going to talk about working with Axon to play a little game, tic-tac-toe. So, so the original idea was to have it play dominoes. I don't know if everyone's familiar with dominoes, but it's you have different tiles, and uh, it's a lot more complicated than tic-tac-toe. It's just the UI is a lot more complicated, so I moved on to something I thought would be simpler, which is a tic-tac-toe. And I will just demonstrate it very quickly so that we can see.
Uh, Del Marcos, I I think I see you only your Discord window.
Uh, oh, really? Oh,
Yes, you
let
can share.
me share something else. Share. Oh, screen. Okay, sorry. I was showing the application. There you go. Okay, now everyone can see my whole screen.
Yes, your screen now.
Okay, sorry. I'll start over. It wasn't that much. Um, so this is a lecture about machine learning with Elixir using the Axon library. Um, and the original idea was to add machine learning to a dominoes game that I was starting to write. But that dominoes game is very complicated. UI is very complicated, and the strategy is complicated. So I decided to do something simpler, which is use machine learning for tic-tac-toe. And I'll demonstrate a little bit of the game. Hopefully it started. Let me know if my font is too small. I like small fonts. It is a little too small. Um, so so it's like tic-tac-toe, but instead of X's and O's, I use emojis, and instead of and also the moves disappear, so it only remembers the last three moves of every player. So it's a little different than regular tic-tac-toe. And the other idea was that instead of just two players, I could have maybe four players, five players, and just make the screen bigger and see if I can have the machine learning um, still work with a lot more players. But uh, with more than two players, it's very just random. There's no strategy here. It's kind of just randomly clicking around, trying to hope that someone else messes up. So I really just stick to the two player. I focus on the two-player game. And if you have any questions, just I guess let me know in the chat. I'm not looking at the chat, so if someone can let me know if there's something in the chat for me to read. Um, so with Elixir, there's only two deep learning options. There's reinforcement learning using the Stockyards RAN library, and there's deep learning with Axon. And reinforcement learning, the difference between these two, reinforcement learning is, so let's say you wanted to learn any game, tic-tac-toe or chess or whatever, dominoes. Reinforcement learning would start learning from zero, from the first move to the last move. So it would start with in this case, it would start with empty grid. The first move would be, this O on the left side, then X, then O, then X, and it would learn from many games uh, what the best moves are. And with deep learning, you can't do that. Deep learning, you're basically just I'm treating it as a classification problem. So in the example from Sean Moriarty's book about Axon, he's using an example of training Axon to learn images of different animals. So in the training set, there's pictures of dogs and cats and different animals, and then you show it a new picture, and then it tries to predict, uh, tries to guess what the animal is based on the training data. Um, so I'm doing a similar problem. I say, based on the current positions on the board, what is the best move? So this is an example of a board position that I'm using. Um, so the input would be this board position, two O's on the left, two X's on the right side. Um, I convert this grid to an input, which is really a one-dimensional list. It's just a list, a flat list. Um, and then there's some hidden functions that happen in between, uh, and it converts all of that to the output, uh, which is the prediction of what the best move should be. Um, so that's how I'm not really explaining this hidden part yet. If I'll get to that towards the end if someone has questions. But the idea is that the shape of this grid with the current positions is the input, and then it gives me a prediction of the best move as the output. Um, so the first thing to do is to format your data in such a way that you get is basically just have good data logging. Um, so I wanted to log everything that represents this grid um, so that I can pass it in as input to the deep learning function to the deep learning model. Um, so for this example, this is how I'm logging the moves. So I'm storing the current positions on the grid and the oldest move, which would be the move that's about to disappear. If you saw my demo before, pieces were disappearing. So that's stored in this array, in this list. And then this is the prediction of the next move, of the best move available. So translating this grid to this input, so 000 means it's not taking, so 000. So I'm using, so I'm translating this grid to an array of from 0 to 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. Those are the positions in the grid. And then this first list will be what positions are taken on the board and by which player one or player two, or by no one. So 000 because no one's taken that position. 112 because 112, 122, 122. And then the next list would be what is the move? What are the pieces that are about to be removed from this list, if any? So 000, nothing is about to be removed. 101, 1 and 1, these two pieces are about to be removed. And 000 because none of these are about to be removed. And based on this shape of this grid, the positions on the board, um, position 2 is the best move for player 1, which would be right here. And all of the logging that I'm doing is from player 1's point of view. Um, so the result will be what should player 1, the next move for player 1, what should that be? Um, and then so I have to translate that tuple, Elixir tuple, to something that the uh, Axon library would understand. So I can't pass in a tuple, so I have to pass in a one list, and that list has to be. So I can't just pass in 0, 1, and 2 because the deep learning algorithms won't understand what 1 and 2 mean, or if I have 5 players, doesn't understand 1, 2, 3, 4, 5. That means 5 players. So I have to translate it. So the better thing to do would be to translate those all of your inputs to zeros and ones to binary, which it's called one-hot encoding. You translate it to zeros and ones, if you can do it. Sometimes if you have decimal places as your input, you can't do it, but in this case, um, I can do it. So I am translating all of these, all of the positions on the grid to zeros and ones. So this is my translation, how I translate this grid to this large list. Uh, so uh, so so this is still 000. So this is means that it's not taken. So 0100. So 0100. Zero not taken, not taken. The first three are not taken because on the grid they're not. No player has taken that position. 1000. It's this one. It means that piece is about to disappear. So this piece is about to disappear. 0010. Map it 0010. That's player one. That's their piece. And then this is about to disappear. So that's 1000. So it's about to disappear. Underscore means it's about to disappear for this grid in my presentation. And then the same zero. This is 0010, 010, player two, and so on. Um, and then also I have to train the model on different variations of the same grid. So in the example in the book, in Sean Moriarty's book, um, where he's training the model to detect different types of animals, cats and dogs. Uh, you can't just give it, you have to rotate the image left and right and upside down and flip it left and right so that it learns that all of these images are the same image. It's an image of a cat, but you flip it upside down, rotate it left and right. It's still the cat. So the same idea here. This is the the grid from before, and all of these around are the variations of the same grid. So I'm rotating them and mirroring them. So this grid, if I flip it left to right, I get this input. I get this variation of this grid. If I take this grid and rotate it and flip it, it's the same grid. So it's 1, 1, 2, one disappearing, two disappearing, so one disappearing, two disappearing. It's the same grid. This is mirrored upside down. This is mirrored. This is a mirror rotated to the left 90 degrees, and then this is rotated uh, left to right and upside down. So these are all the same grid, and it should learn uh, all these variations so that it can make a better prediction. Um, any questions so far? Anyone? Um, so for training, before I was talking about how to model the data, and now we get into the training. Um, so for training, I tried to have it play itself. So I would have two untrained models, um, and because of the way the game is going, the pieces are disappearing. Um, this game, in reality, it could never end with two very good players. Um, so for this case, I would have a lot of games that would never end. It would just go, pieces would disappear, and then just players, it would never make a winning move. So I had to limit the game to 50 moves, and then that 50 moves, it would just be considered a tie. So um, I didn't learn anything, and my program didn't learn anything either. And then the next thing I did was to create a simple opponent uh, for my model to learn from. So I created a very simple opponent with simple rules. So the first move, take the center. Uh, or if it's on the second move, basically always try and take the center. If it's the first move or the second move and the center is available, um, take the center. Uh, Otherwise, go for the win. So try and get three in a row. Um, Go for the block. So prevent the other player from getting three in a row. And otherwise, just play a random move. Um, and then, so this was better. So our games ended, but there was too much data because games would last for 40, 50 moves. Um, and uh, a lot of those moves were not winning moves. So there was a lot of noise in the data. Um, so then I decided to split the gameplay into three stages: opening moves, blocking moves, and winning moves. Um, so opening and moves and blocking moves are mostly the first six moves of the game before pieces would disappear. So I would train that myself, and then so opening moves, blocking moves, first six moves, and then the winning moves would be everything after that. So move number seven up to until move number 50. And then I would ignore losses, ignore the losing moves, and ignore the ties. Um, so I would sometimes train the untrained model against the simple opponent, and then sometimes I would use the data from the simple versus simple um, to get more variety in my training data. I'll show you the training data in a bit. Um, and yeah, so now I'll demo a little bit of the code and a little bit of the game. I'll just look at the chat real quick to see if there are any questions. No questions. Can everyone see is my font size okay? I like small fonts. So is, so, and this is code. I didn't share it at the beginning, but I'll share it now. All of this code is on my GitHub. So if you want to play along, you can see the code. Uh, so I'm looking at the training data file. So this training data file has the moves that I have trained myself manually. So it's moves 1 through move 6, and there's no other moves. So the first move is uh, it's a little easier if I show you. So this is the training data for move 1, and I'm just printing it in a ASCII art form. Uh, so this is training move 1. So there's no one has taken any moves. Uh, no pieces are about to disappear, and it should take the center square. So that's move number 1. Take the center square. And then for the second move, uh, so the rules are in the training data. So uh, if the opposition has taken uh, the corner, so any corner, um, then play the center. So taking the corner, nothing will disappear, and take the center. And then same for here is this is if the opponent has taken the side, any side, because I'm going to rotate it, uh, then and nothing's about to disappear, then take the center. Um, and then this is if the opponent has taken the center, then take any of the sides. Uh, so that's the center, nothing will disappear, take the side. And I'm going to rotate it so it could be any side. And then, so I'm doing this for all of the first six moves. So I'll just do a little move ahead and to move, say, let's say five. So this is the fifth move. So four four pieces have been played, two by player one, two by player two. Um, so then, in this case, uh, player one should finish the taking the winning move. So this is all take the winning move, winning move, winning move. So this is a lot of just me manually uh, logging and training it to take the winning move or play blocking move. So in this case, this is a blocking move. So player two will win if player one doesn't play here. So player one should block uh, player two from winning. And uh, and this is not a winning move and not a blocking move. It is just the best move. Based on me playing, it's the best move for player one to make. Uh, Player one should take that so that on the next move it can play here, play there for the win. Uh, so that's me training it for the first six moves, and then after that, just take some random data. So this is the load function in case anyone wants to see this. So it's just reading the file. There's a file with training data somewhere in here. And it's just going to read that data and load it into memory. It's in the same format as this move. This is just a list. It's just another list that I'm saving to file. And just taking a look at this is the data that's from the CPU playing itself. So this is so these single quotes means that this piece will disappear. So this piece will move for player one, and this piece will disappear for player two. So if it sees this type of shape, the best move for player one is to block player two from winning and go for the win. It's actually a win for player one. And then in this case here, I don't. So this was not a winning move or a blocking move. It's a setup move. So player one should play here because this piece will disappear for player two. And then player one can play here and go for the win up the middle. And then in this case, this is the same idea here. So player two's piece will disappear. So player one should play the corner so that it can win the diagonal. So hoping that made sense. And so that's the training data. And let me just go into the model really quickly. So this is the model. This is how pretty much everyone who uses Elixir will model it. I think we're all using the same example from the library. So the input would be there's whoa, that's annoying. So for the prediction, it takes in a model, a state, and a tensor, which is just the data like this here, which is the current state of the board. So the model for deep learning, a model is not like a model in React. It's not the state of the game. A model in deep learning is a function. So in this case, the model is Uh, it's this. So it's similar to what I showed in the diagram here. So I have an input here, which is a flat list, and then I have three hidden layers. I only have two in the diagram. Uh,
Then Marcos,
so
can you
yes,
zoom this code?
yeah, better.
Yes, yes.
Um, so this is the model. So input is just the flat list here. Um, and then I have uh, three hidden layers. So I have two in the diagram, but I'm using three in real life. And then the reason you would use the hidden layers are kind of for if you want to train it on nonlinear data. So I'm stealing this diagram from the MIT course. Let me make this bigger. Oh, I can't play it. Let me do it this way. So let's say you have a very simple classification problem, and you want to split this data into the red pieces and the green pieces. Without activation functions, you can only just the this deep learning would only be allowed to draw a straight line between the data to try and split this data into two groups. Um, but so that's why we use uh, hidden inputs, which are introduce activate, which use activation functions to introduce nonlinearities. So this is the same to data inputs as just if you use activation functions and hidden inputs, you can discover a better way to partition your data, so you can have a better classification. Uh, so my simple example, I'm using three activation functions, three hidden inputs. But for something like self-driving cars, you would have thousands, millions of functions, of activation functions. Uh, so the more you have, the slower the training will happen. It's just the way it is. And these are just different ReLU6 and softmax. Those are just different types of activation functions. Um, it's I don't really go into that because it's very complex, but in the README, uh, towards the bottom, uh, this is a good course into deep learning. It's but if you want to really, really learn it at a higher level, this is the MIT course. It's free. It's on YouTube. It's about 10 hours. They update it every year. Um, but it's very, very, very detailed, and it's very, very, very good. So it goes into explanation on what onto deep learning and more and other topics like reinforcement learning and things like that. So it's a very good course. Um, but back to the lecture. So I'm using three activation functions, three hidden inputs. So this is my model, which is just a function. Remember, your model is a function. So I take in the model. The state is so when I train the data. Uh, so when I'm using my training data to train my deep learning model, it creates a state. So that's this function. So it's training based on the training data. So it takes in the function, which is a model, and takes in the training data, and then it creates a state so that it's basically learning all of the different shapes, different positions, all of the positions from the training data, and it learns what the best move is from all of this training data. And uh, so when I make a prediction, I pass in the model, I pass in the state from that train, from that it learned from here, and then I pass in the data, which is just the current state of the board, and it will return a prediction, and then the prediction will be, let me just show you. So it learns that the best move, uh, based on, I just took the center, so the best move for it to make would be to take the side, um, any side. So the prediction from this predict function is a list of weights and positions. So it's saying that uh, this is the weight. It's a tuple, and the first thing in the tuple is a weight, and the second thing in the tuple is the position. So it's saying position 3 has the highest, has the best weight. It's really all of the sides. So the first 3 moves are the sides because I trained it to learn that. Um, if we go back to the training data, I trained it that if the center is taken, take the side. So it's saying uh, the first, uh, the best moves are to take the sides. Um, so because I'm training it and I'm training it to rotate so I'm training it on different positions. So I'm training it with, so in this case, I would train it with take uh, this side, take this side, take this side. So I'm passing in 4 different variations of this data so that it can learn uh, what move to make. And that is the prediction. And let's see what else is there. And I think it should mirror. So it learned how to block. So it's trying to win here. I'm going to block it. It's going to try and win there. So it's really good at learning what to do. I don't know what the best move is for me. Yeah, so this is going to go on forever. Oh, no, maybe. I don't know. But in any case, yeah, so I think that's it. I don't know if there's any questions. Um, I think that's my presentation. Let's see. Game on training data. No. Any questions?
Anyone? Some questions? Take 10 minutes to talk with the Marcos. You use the hand options to talk. The MIT course is on the YouTube, right?
Yeah, so I put the link in my README. So YouTube has the video, but you should go to the website because they have the PDF for the course. It's- I thought they had the the slides. Yes. Oh, yeah. So the slides are underneath each video, so you can download the slides for any of the videos. So this is very detailed, deep computer vision and whatever. But yeah, all of the videos are online. All the slides are on this website. So better to go to the website first and then watch the video, which goes to YouTube. It's a playlist that they update every year. Playlist, new playlist. So they just updated it for 2025, but it goes back to 2018 if you want to watch. This is a lot of videos. It's probably 100 hours of videos. 80 videos. Yeah, it's a lot.
Besides the MIT course, where do you recommend to get a better understanding of deep learning and machine learning? have prerequisites to understand?
Uh, so if you just want deep learning, this video is pretty good. If you, it's this playlist on YouTube is pretty good. If you just want very short videos that are just to get an idea, an understanding of what neural networks are and what all of these things are, it's very good. Um, but if you want to learn with Elixir, then you can try Sean Moriarty's book, which is about the Axon library. Axon has pretty good. I should. I do. Oh no. Oh, I'll have to fix that. Uh, Axon. They have very good notebooks on uh, on how to use the library. So if you run these, you can learn some. Um, and yeah, I mean that's basically it. I threw in this web page has this is where I read he describes how he modeled his game. So I stole um, some ideas from this GitHub project. He's using reinforcement learning. I cannot use reinforcement learning because Elixir doesn't have it. But I stole some ideas about how to shape the data, how to model the inputs so that I can get a better result, a better predictions.
Nice. I really like your presentation. I see your presentation in Denver Meetup,
Hmm.
and
Yeah, the link to to that meetup is in the
Okay, well,
is in the README if
do
anyone
you
wants to watch.
do you have a plan to make the other presentations about the machine learning?
I don't know. I only did this because I had time to learn it. And I used a very simple game. And yeah, so it's a lot of I don't know if I will. If I have a good problem that I want to solve, then I will, but I
Um,
don't know if I will do that.
do you work in a company today?
No, I got laid off in December, so I that's why I had time to do all of this this example.
Okay. Can you share your contact if some
It's
companies?
in it's in it's in my GitHub. Idea Marcos. My Idea Marcos over LinkedIn. Same Idea Marcos. Um, same guy. Same image.
ID Marcos. Nice.
Idea Marcos. So
Connect with ID Marcos on LinkedIn. Create a big network, an ecosystem Elixir.
um,
Someone have other questions? Awesome. Okay, continue this meetup. Uh, Now it's turn Paulo Valente. Paulo Valente to talk. Uh, okay.
hello. Can you hear me?
Yes, yes. Can hear me.
Okay,
Can hear.
let me turn on my camera. And I just need a few seconds to open the presentation. Okay, so let me share my screen now. Is everything okay? Can you see the browser? Is my voice okay?
Yes, is voice okay? And your screen is okay too.
Okay, so let's get started. I gave a version of this talk at Codebeam Light New York last year. So you
Hello guys. I I think the my internet's not that nice in the moment.
Oh, everyone dropped the cow? I dropped it too.
Yeah, I think it was a Discord bug. But Paulo, you still here? Can you send a message on the chat?
He's in the audience. He's raising his hand.
Yeah, I think it was a Discord bug. So Mateus, if you can please put Paulo back as a speaker.
Moment. Some moments. Keep it calm, keep it calm. Okay. Paulo Valani return. You can't hear me?
I can hear him.
Anyone can talk something?
I can hear you, Mateo.
Yes. I hear you too. How much doubt any story bug happened now? Yes, I chose the Discord because it never have problems with Discord. Uh, not I cannot hear you. You can hear me?
Mm,
Ah, what?
I can hear you now, Mateus. Can you hear
Yes.
me?
Yes.
Okay.
Your
Okay, so
speak is
I'm
good.
gonna just restart presentation from the beginning. I think it's easier. So I should be sharing my window now. Can you see my browser?
Yes. See your browser.
Okay. Okay. If anything happens again, you can just message me on Slack, and I'll be able to see the message on my phone. Okay, so let's restart this. Today we're gonna talk about image processing in the browser with an X. And before we get too far ahead, let me introduce myself. I'm Paulo Valente. I'm Brazilian. I'm an electronics and computer engineer. And I've been working with Elixir for the past 7-ish years, a bit more than 7 years now. And most importantly for this talk, I am part of the NX core team. And today we're gonna discuss what are matrices, which are the main data structure that we're gonna use during this presentation. And then we're gonna get into more details of what an X is, and then how we can operate on images on the computer, and a few specific things for image processing, convolutions, kernel filters, and then we'll discuss a bit about 3 types of filters, and then we'll get to a live demonstration plus a pre-recorded surprise that I have as well. And let's get started again. For understanding matrices, we just have to think about them as a collection of numbers. We have a number, which is what we learn in school, and then a vector is just a list of numbers for the purposes of this talk. And a matrix, there are many different ways we can think about matrices. We can think about them as lists of vectors, and they can be like column vectors or row vectors. Or you can just think about them as a 2-dimensional collection of numbers. And then there are a few specific mathematical operations that you can apply to matrices. And they have their own mathematical rules. We don't have to worry too much about those. We can just cross that bridge when we get to it. And NX stands for Numerical Elixir. It is the main numerical computing library for the Elixir ecosystem. It is inspired by the Python ecosystem, and it brings to Elixir the multidimensional array data structure that we call the NX tensor, as well as the ability to deploy computations to the CPU, GPU, and we're gradually working towards distributed computation as well. So in the previous talk, we saw Axon. Axon is the library for neural networks, and Axon works on top of NX. NX is this foundational layer for machine learning and numerical computing in Elixir. And an X function would look something like this, where we import an XFN, and that module will bring us the defn macro, and that macro will bring some specific capabilities to Elixir, where instead of just running the code as is, calling an x add, an x cosine, an x sine, that fan will be able to group those computations in a computation graph. I won't get too much into this, but we
Paulo,
can. Okay.
On the moment, your slide is freezing in first page.
It is.
Yes.
So let me share it again.
See you 6th page now.
Oh, so we're back.
Yes. If you
Okay.
restart your presentation.
Let's restart again. Maybe. Okay, let's try this again. Just let me drink something to recover my voice. Okay, let's just pretend this is on the third time. So today we're gonna talk about image processing in the browser with an X. And before we get too far ahead, I'm gonna introduce myself. I'm Paulo Valente. I'm Brazilian. I'm an electronics and computer engineer. I've worked with Elixir for the past 7 years, and for this talk, I think the most important part is that I'm part of the NX core team. And in this talk, we're going to discuss a bit of the prerequisites that we need to understand image processing. So we're going to go over what are matrices, and then what is NX, how computers represent matrices, and then we're going to discuss a few important operations that we need for image processing. And then we're going to go into a live demonstration. Plus, a small surprise that I've also recorded. So, matrices, you can think about matrices as a collection of numbers. You have a number, and then if you group numbers into a list, you can call that list a vector. Vectors aren't necessarily just lists of numbers, but for the purposes of this talk, I think we can just think about them as that. And then matrices are just the two-dimensional extension of that. So it's just rows and columns, and numbers are organized into that table-like structure. And NX is the numerical computing library for Elixir. It's what enables Elixir to do numerical computation in a competitive manner to Python. It is inspired by NumPy, JAX, and all of the Python ecosystem. And the most important part is that NX brings tensors, which is a multidimensional extension of matrices that we just discussed. And also, it allows deploying code to the CPU, GPU, and some other specific types of hardware and runtimes. And then NX is the base layer. In the previous talk, we saw Axon. Axon is built on top of NX. So everything that we're going to discuss about NX also applies to Axon to some extent. And now we have one of the simplest examples we can see for NX. So we have a module, and at the top of the module, we're importing an XDefn. And by importing an XDefn, we gain access to the defn macro. And the defn macro works mostly like a normal Elixir function, but it's gonna have some overrides, and most importantly, it's gonna be able to group all of the computation that's defined inside it into what we call an XDefn expression. We're not gonna get too much into what an XDefn expression is, but just know that that is one of what enables NX to do what it does. I just realized my camera is off, so I'm gonna turn that on again. So here we have some example function calls, and notice that we can call it with numbers, tensors, some combination of those. And as I said, NX will group the computations in a nested NX-defn expression struct. And then when we call the function, it's gonna compile the code into the defn expression, and then it's gonna be executed or compiled before executing through configurable compilers. And then different compilers will be able to target different backends. Sorry, will be able to target different devices. And the compilation of an X code happens at Elixir runtime. It's what we call a just-in-time compilation. And through NX, ERI, EXLA, EMLX, we're able to access different devices. So we can deploy to CUDA GPUs, to the Metal GPU on Macs. We can deploy to the iOS GPU via NX ERI, and we can also deploy to the browser using NX ERI through to column 5, that's going to have 4 channels. That's one way of thinking about it. And then there are other formats that have fewer channels. So grayscale will have either just one channel if it's just a black and white image, or maybe 2 channels if you want to have the alpha channel for transparency. There's a lot of flexibility on how to do these representations. But generally, images are a matrix or a collection of matrices where each position represents the intensity of the color or the channel that you're representing. And then for image processing, there is this mathematical operation that I'm going to first describe and then we're going to see in action, which is the convolution. And the convolution applies a small matrix that we call the kernel to each part of the matrix, and then it slides over the kernel over the input matrix. And that yields a new matrix that's kind of like a weighted sum or a local weighted sum of the input matrix. And that's used for a lot of things. It can be used for edge detection in classical image processing, and that doesn't use neural networks. It can be used for blur, sharpen, which is kind of the opposite of blurring. And these last two are what we're going to use today. So here is a small animation of the convolution at work. And we just get the kernel, slide it over the input, and we just put the result on the output matrix. This is a very simplified representation of what a convolution is, but this is what we need to visualize when using it. And then, if we have the convolution, we have this subset of image processing, which we call kernel filters. And then the kernel filters are just special kernels that we can define that we know apply a specific operation to the matrix. So the uniform blur, we can notice quite quickly, it's just the kernel is just a matrix that has all positions equal to each other. And this weird number is just because we always want the kernel to add up to 1, because it's kind of like an average. So the 0.0204 is just because this matrix is 7 by 7. And then if you do 1 over 49 in this case, you get 0.0204. The Gaussian blur is another type of blurring that's more flexible. And in this case, we have, you can kind of see it symmetrical over the center just by looking at it. You don't have to worry too much about how this function is defined. You just have to imagine that it's like if you have a small mountain that's really smooth and centered at the middle of the matrix. And then if you add up the matrix, add up all of the positions, you'll also get 1. And the Gaussian blur has more parameters than just the size. It also has a sigma that will tell us how flat or how high that mountain is. So it will concentrate or make it more diffuse. And then sharpen, it's a bit harder to visualize, but it's just you get a matrix that has 1 at the center, that's the delta, and then you get 2 times that matrix minus a blur kernel. In this case, I'm using the same blur kernel as the Gaussian blur. So you see, for instance, the second row, second column is 0.0209. It's the same value there, just negative. And the sharpen can be thought of as if it were the opposite of a blur, like the inverse operation. Not quite that, but it gives us the basic idea. And then let's go to a live demo where we'll be able to better visualize these things. So I'm gonna stop my camera on Discord and allow the browser to access it. And now we have at the left the input image and on the right the output image. And when I select a filter, I can see as NX compiles new code for the filter, I get a notification at the top right. So I got a new update there, and we can see that as I increase sigma, as I increase kernel size, the output image gets more blurred. If I go to the uniform blur, we'll see that it behaves a bit differently. So it needs a larger kernel size to get the same level of blurring as the Gaussian blur. If I go back to kernel size and really increase sigma, we'll see that it's quite a bit, or at least a bit more blurry than the uniform blur. And sharpen, we can now see that it gives more of a crispiness to the image. It's the best way I can describe it. If we go back and forth between the Gaussian blur and sharpen with the Gaussian blur kernel, we can really compare how one is kind of the opposite of the other. And I've also added a tint filter here, which is just a way of colorizing the image. And then for the tint filter, you'll notice that it doesn't keep recompiling, because as these are just weights and the shape of the image and there is not really a kernel at play here, we can just use the same NX function for each one. In the case of the other kernel filters, we need to recompile basically one NX function for kernel size. And then we can really colorize our image here, or just slightly by changing the alpha channel of the tint filter. And going back to our presentation now, I've also recorded basically the same code. It's not quite the same because I didn't support tint, but this is running on device on my iPad. This is just a screen recording of my iPad, and I'm interacting with it in real time as well. And the nice thing is that this code is actually running on device. The only data that travels between the server and the device is the compiled bytecode, because NX is compiling things on the server. But there are no images traveling out of the device. It's just happening on the iPad with Live View Native. And this is the small surprise that I had separated for you. Um, so we've seen how matrices and kernels interact to produce image processing. We've seen NX in action, especially NX being deployed to the client. And by deploying to the client, we avoid consuming too much bandwidth. After it's a lot cheaper to just send the bytecode in terms of bandwidth, to send the bytecode and then to, instead of sending the bytecode, sending images over and over, especially if you're gonna process basically every frame. And yeah, there are quite a few interesting applications that can arise from this capability. I've shown image processing, but you can do basically anything that you can with an X on the edge. And the code is available on my GitHub at this repository. I'll share this on the chat as well for people that are watching live. And yeah, thank you. You can reach out to me on X and GitHub, LinkedIn as well, same handle, and Blue Sky, it's Foveland.social.
Nice, Paulo Valente. Thank you for your presentation.
Mm-hmm.
Amazing, amazing.
Does anyone have questions?
I have a question. I can use NX to compress image.
Yes, there is. Since we're in the browser, let me go to Scholar. Actually,
Because in my project, the feature is streaming video, but not works with full quality videos. I think about compress.
right. So there are a
Mm.
few ways of going about this. If you just want to compress to reduce bandwidth, you probably just want to resize the image and then do the downsize it and then upsize it on the other end. And for that, I would say eVision is the way to go. eVision is the library that binds OpenCV. I'm not sure if I can. Yeah. So eVision is just OpenCV bound to Elixir, and it also has an NX interface. So you can interoperate eVision with, let's say, classical NX. And if you just look for how to do things with OpenCV, it's quite easy to translate the Python OpenCV code to what would be the eVision code. There are a few conventions that you learn quite quickly when trying to do these types of translations.
Nice.
And then, yeah, I would recommend eVision.
I research about these things. Can we use NX in computer science as well, leveraging the Erlang cluster to distribute heavy computations?
So, not quite yet. If we go to the Elixir NX repository, you're gonna see that recently I merged this pull request, which is an XDefn graph. And this allows us to take an XDefn expression and using some split rule, we can split that function into stages. And the stages are basically just what we intuitively can think about. So if I split on the dot computation, it's basically gonna take and turn all of the arguments to the nx dot function into arguments to a new function, and just create a divide into the graph there. And this is one part of the puzzle. The other, which is currently just as a proof of concept in this pull request, is that we can then take a graph and allocate it throughout an Erlang cluster. So if you go to this open pull request, the final test here, it actually shows us taking an XDFN expression, creating a graph of an XDFN expressions, and then running that graph across two Erlang nodes.
Nice.
And this is soon gonna become a library that's more generic than just for NX. But then we can use it to, let's say, coordinate distributing load between two GPUs on the same machine, or distributing NX computations over different machines, or even if we get too crazy about it, we can run part of the NX code on the client as well. So what I just showed with WebAssembly or deploying to the iPad, but connecting that with a larger computation that happens throughout a Beam cluster. And I'm also working on deploying NX with Halo AI acceleration to nerves. So that also brings nerves into play here. And for people who don't know, nerves is how we can run the Beam on embedded devices such as the Raspberry Pi.
All right, thank you. Have some question? Anyone? Anyone else? Question for Paulo Valente. Where do you live in Brazil, Paulo Valente?
I live in Rio.
Rio.
Yeah. Copacabana, actually, so Lady Gaga is just over there.
Uh, Someone will write a question for you on the moment.
Yeah.
You can read it or only sharing it?
Oh, I have the Discord window open right now, so I can see that people are typing as well.
Gaga likes Elixir too. Oh my god. João writing the Bible? Stop typing now. The viability of using Raspberry Pi with Erlang Elixir is something I really like.
Yeah, I'm giving a joint talk with a friend of mine, Vittoria, in Codebeam Stockholm on June 2nd, I think. It's early June, so basically in a month. And we're at the final stages of getting things to work such that you can use like eVision, EXLA to run regular NX code on the CPU, but separately you'll also be able to call into full-on models with the Halo AI hat. The Halo AI hat is basically an accelerator that can run let's call them closed models, as in you can run YOLO for object detection, but you can't really deploy arbitrary computations to the device. So the way I see this happening is that we'll have a subset of things that run on the hat, and then you can use NX to communicate data in your pipeline and then have those models at the core of your pipeline. But you can also think about, let's say, taking a Raspberry Pi 0W, such as this chip here, which is a lot less powerful than a Raspberry Pi 5. And then you can use like similar devices to that, cluster them to a Raspberry Pi 5 that's running on site, and then use that as your, let's call it your on-site data center for for computations.
Nice. I
So
think
yeah.
about make a big cluster with network with
Hmm.
many GPUs. This works today.
Yeah, it well, maybe by the end of next week we'll have something. Let's see. But um, as soon as we have distributed graph execution working, we'll be able to have rules like um, basically each node declaring how much memory it can hold, and then I can say things like, "Hey, this neural network takes up 100 gigabytes of VRAM, and I have not 100, but let's say 30 gigabytes. And then I have an RTX 4090 beside me that has 24 gigs. That computer back there has an RTX 2060 with 6 gigs. But you also have to have space for the competition itself. So let's also put this Mac into the mix as well, which has 32 gigabytes of shared memory. And by like summing up all of this, you'll see quite quickly that we do have in this room more than 30 gigabytes of VRAM available. And then if you split your computation in a smart way, you can allocate as much as you can on the 4090 and then the 2060 and then the Mac, and have all of them interconnect with the distributed graph executor that I'm working on. And then,
Nice.
yeah, you'll be able
Have
to leverage your home cluster.
have a new question from João.
Mm-hmm.
Can you share the patch for anyone who wants to contribute to the NX project? What do you think they need to know first?
It really depends on what you want to contribute with. We recently have been working on better documentation. So you'll see that there recently has been merged a cheat sheet pull request on an X core, and then I have an open pull request for a cheat sheet on Axon, and then we also revamped the introductory documentation for NX. So I would start by validating that we didn't miss anything there, and then in doing that you'll be able to um, see if you missed anything really, if we missed anything, and then also learn and act in the process. And I think that for NX core it's a bit harder to add things because I wouldn't say it's feature complete, but let's say it's 95% there in terms of what the core library needs. And then the missing 5% are basically too hard for beginner contributors to really tackle as a first contribution. So I'd say start by going through the documentation, submitting pull requests or issues for things that you think are not really um, clear, and then I'd say that the ancillary libraries, so Axon, Scholar, eVision, those might be able to, or EMLX as well. Those might accept or have room for um, more meaningful feature contributions. Oh, and for an Xcore itself, more guides are basically always welcome. You can open an issue if you have an idea and we can discuss there, or you can just ping me on the Elixir Slack or Erlang Ecosystem Foundation Slack. I'm always there. Or actually on the Discord here as well.
Other question for you.
Mhm.
This is a very nimble question, but could it be possible to combine GPU and CPU combinations based on having a cluster of raspberries or
Mhm.
Pi-Is, which AI hat and without AI hats?
Um, as it is today already, you can just cluster all of the Raspberry Pis that you have running nerves, and then it's just as simple as you knowing which ones have the hat, and then uh, let's assume that we've released the an Xhalo library. We'll be able to just run the model on one machine and then on one of the Pis, and then send data over through Erlang RPC between the Pis. If people haven't um, really experimented with this, Erlang RPC is um, sorry, got distracted. I think we want this. Um, so Erlang RPC makes it really easy to do distributed calls over a cluster, a Beam cluster. I think we're basically on time right now, so uh, and my voice is wanting to go away as well, so I think we should stop here. And if anyone has um, any questions afterwards, you can reach out to me and we can talk about those.
Nice. This is good talk. I I have many ideas with your explanation explains. I
Nice.
reuse all all talks today. Uh, Now is my turn to present.
Thank you.
Nice. Thank you too, Paulo Valente. And some minutes because I configure some things. And okay. Presenting. Uh, Now I can't read the chat. I I can't I call some friend to help me because if any problem occur, I can't receive the feedback. Okay,
Hello, guys.
hello. It's clear. Can you hear me? Good. My
Yeah, yeah,
screen
can
is
see
okay.
you, yeah, I can hear you, can see your screen.
Nice. Hello everyone. My name is Matheus Camargo Marques. Today I talk about my project is named AukTalk, pseudo telephone. Um, in this talk, we are going on a journey through time, starting with Ericsson and challenges faced in build telecom systems, the true birthplace of OTP Open Telecom Platform. We will explore the real-world context that shaped Erlang and Elixir as we know them today, and how the need for software real-time gave rise to the robust platform. But it doesn't stop there. I'm going to show you how I build AutoTalk or something close to it using Elixir, an experimental project that simulates communications between devices, embracing concepts like lightweight process, supervision, resilience, and messaging, all which that are old school telecom vibe running on Elixir modern stack. If you enjoy a good story, distributed system, or you've always wanted to build your pseudo telecom project with style, this talk is for you. Expecting a lot of OTP nostalgia and just the right amount of code. Talk agenda, historical context, Ericsson and the origins of OTP. What is OTP and why is it different? My AukTalk project in Elixir, architecture demo, what we learn and why Elixir is still a powerful tool for distributed system. Historical context, Ericsson and the origins of OTP in the 1980s and the 1990s. Ericsson's, the Swedish telecom giant, was facing a colossal challenge. They needed to build telephone systems that were highly available, fault tolerant, distributed, and capable of evolving without ever shutting down the servers. Imagine having a two-patch or UP data system that was handling live phone calls without dropping a single one. They needed to build telephone systems and that were sorry, no DevOps, no Kubernetes, no let's roll out to the new container. That's and see what happens. That's the context in which Erlang was born. A language created by Ericsson's engineers, Joe Armstrong, Robert Varden, and Mike Williams to meet these extremely critical demands. But the language alone wasn't enough. They realized that true robustness comes from patterns. So the questions were, how do you manage thousands of current processes? How do you supervise them? How do you restart parts of the systems without affecting the whole? That's how OTP Open Telecom Platform came to life. A library, a framework that wraps best practices and solid abstractions such as Gene server, process with standardized behavior, supervision tools for handling failures, application, standardized way to start and manage your system, hot code swapping, updating code in real time with zero downtime. In short, OTP isn't just for telecom, it's just a blueprint for building resilient systems in general, but it was born deep in the trenches of telecommunications. This solid foundation, built to meet Ericsson's critical needs, is exactly what we were using today when you run Mix New to create an Elixir project. And interestingly, now it's the very same foundation I use in my experimental AutoTalk project. What is OTP and why is it different? The OTP, the Open Telecom Platform, is more than just a library, is a mental model for building reliable and resilient systems based on the philosophy that failures happen and that's okay, and as long as you are prepared to crash and recover fast without drama. While most languages and frameworks try to prevent the system from breaking, OTP says, let it crash, but crash the right way. What is the never complete crash because each part runs in isolated lightweight process. Recovery automatically from failures, thanks to supervision trees. Swap code in real time with zero downtime. Scale horizontally with distributed process almost effortlessly. Are easy to test and compose using standardized behaviors like team servers, supervisors, applications. OTP as built from real-world battle experience, patterns learned in productions dealing with millions of simultaneous phone calls. That's why it is not just different, it's truly battle tested since the last century. When you create a Gene server, you are using a design pattern crafted by engineers who could afford to fail, because a single bug could take down an entire country communication infrastructure. And that solid foundations is what allowed me to build my own pseudo telecoms system in Elixir, simulating a digital walk-talk using messaging processes and supervisors, all following the same OTP principles and patterns. One moment. This is my project. Can you enter in my project, please? Someone. I have some friends.
Hello. I'm here. You're just not seeing us.
Ok. Uh, João, Mário, Navy, working with me. I can talk with you. Can you hear me?
Can anybody hear me?
Hello, 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 hello.
I can hear you perfect, bro.
Hello, hello.
Hello, bro. How are you doing?
Can you hear me?
Can you hear me?
Yes, bro.
I'm going to present a project that demonstrates the real-world powers of Elixir and Phoenix Live View. It's called AutoTalk, As the name suggests, it's a real-time voice communication system, like a digital walkie-talkie, but running directly in the browser. In height-level architecture, the system is based on three major pillars: microphone audio capture, network transmissions between nodes, reactive web interface showing who is speaking, and enable chatting. Um, Show some diagrams. When a user click start transmissions, we activate a module called microphone driver. This module uses system level tools such as AirCord on Linux or SOX on Mac OS to start capturing microphone input. The audio is split into small chunks, allowing continuous real-time streaming. Each chunk is published to a topic using Phoenix Pub Sub, which acts as internal messaging hub. Distributed node communication. This is where Elixir distributed nature really shines. Each applications either automatically via DNS cluster or manually through node connect. A dynamic supervisor sender dynamic supervisor spawn sender process for each connected node. Each sender subscribes to the local pub sub. Oh, no problem. Local pub sub topic and sends the audio chunks via RPC cache. This is a sender. What the hell? Okay. Well, same problem in my drawing, but no problem. I use the RPCast, which perform asynchronous remote procedure calls between nodes. On the receiving end, a receiver process gets the chunks. This is receiver process. Get the chunks, plays each using assistant tools like play, publishes an event node speaking. The receiver sends to chat pub sub. It communicates with live view walkie-talkie process. Web interface. The front end is built with live view, Phoenix live view, so everything is reactive and in real time. Users can see who is online, see who is speaking, start and stop transmissions, and chat via text. There is no need for complex JavaScript to handle UI state. And talk about resilience and observability. All core components are supervised using standard OTP supervision trees, including drivers, senders, and receivers. If anything fails, it's automatically restarted. For observability, we use AppSignal to track metrics. For example, we track upload volume and the download. When this gives us visibility into network usage per node. Network infrastructure, which is tier, to simplify peer-to-peer communications between nodes, especially across different networks, nets, and firewalls. We use zero tier as virtual private network VPN layer. Why zero tier? Emulates a layer 2 LAN over the internet, automatically handles net transversal, eliminates the need for port forwarding using SSH tunnels or traditional VPNs, ensures node.connect works as if the nodes were on the same subnet. Each device joins the same zero-tie network and is assigned a virtual IP. We use TCPs in your node discovery and the connection logic. This makes distributed communications reliable across cloud, home, and edge environments. For example, a Raspberry Pi running in Curitiba and a cloud VM in São Paulo can communicate seamlessly using their zero-tier IPs. Their LAN nodes connect directly, enabling real-time audio transmission without manual network configuration. I have a sequence diagram here, but not explain full this, but a full sequence diagram illustrates the system flow from the user clicking start transmission to capturing audio, streaming it across distributed nodes, playing it back on the destination node, and updating the web UI in real time. I have some real world use cases on site. Teams distributed across a large areas, university, campus, or industrial complex. Lightweight, low-cost intercom solutions for sectors in a company. Remote coordinations in logistics or events. I have some technical highlights. Low latency via small chunks, audio chunks. Live view simplifies front-end logic. I use distributed messaging using RPCast, but I see some things to upgrade this in gRPC UDP, but is have other thing is better to use. I received this update recently. This project is cross-platform support, Linux, macOS. I have new PR in this project to use in Windows architecture system. Fault tolerance architecture with OTP supervision, built-in scalability from the Debian VM, uses zero-tier VPN for seamless global connectivity. Final thoughts. This project shows how you can blend the real world with audio and network communications with the functional ecosystem of Elixir. And the result, a system that is simple, resilient, and clean, even in a distributed real-time environment. What did we learn from all this? Building a walkie-talkie might seem like a hardware project or a nostalgic experiment, but deep down it's a reflection of what OTP has always aimed to solve: distributed, reliable, real-time communications that's fault tolerant. With these projects, we were able to see that Elixir isn't just pretty, is powerful, not only because of its elegant syntax, but because of the solid foundations it carries from the trenches of telecommunications. OTP is more than an acronym. It's a system building philosophy that embraces chaos, which survives it with grace. Supervision works in practice. We didn't have to reinvent the wheel. We just used the patterns that come already made: Gene servers, supervisors, applications, and they simplify work. Distributions is simple when you use the right tools. Zero Tar showed us to we don't need to struggle with net firewalls or complex network. The combination of Elixir plus smart VPNs give us superpowers to connect anything anywhere. Phoenix Live View isn't just a front-end toy, it's a real ally for reactive interface without needing to dive into heavy GS frameworks. The bean is the real hero. Designed resistance which distributed process, resilience, and the real-time communication um, efficiently on the same VM that was originally built to handle critical phone calls. At the end of the day, this project is a love letter to what OTP represents, not avoiding failure but embracing it with structure. If you are living here with the desire to explore Elixir, build your own distributed system, or even rescue old ideas and give them a modern twist, then mission accomplished. As Joe Strong once said, the world is concurrent, things fail, use Erlang. And now we can say the world is distributed, the ideas are old, use Elixir. Uh, I, ha- I have some acknowledgements for Kevin Matthew from India, is my new friends. Yeah, I I know he working together in this project. Other people acknowledgement: João Victor Ferreira Palha, second people to help me to create this project and save my time to me prepare to this presentation. I am Matheus Camargo Marques, I founder of Web Engenharia Cooperative. I have next features in this project. Uh, is exist open telecom platform. I think about create open cooperative platform. Your different lies in your method and your collaboration. You are all engineers and we are not afraid of problems. I have features I specialized in on domain experts, real-time events, new clients, new partners, etc. Calculate team power and team profits. I have research areas, real-time event system, event-driven microservices, active design patterns, event-driven architecture, design event-driven systems, evolutionary architecture, OTP bean studies. A little about myself: I am surfer, I am guitarist, I am peace, I skateboarder, and I always surrounded by good friends who makes me want to be better every day. Uh, Connect me if you want to improve your OTP superpowers, if you want to make partnerships, if you want to be my client. I have 50 developers in focus on Elixir, Erlang, C++ stack. If you want to talk with me anytime, anywhere, if you want to grow your network. That's all for today, folks. Contact me on my email. My nickname is Mateus C.A. Marques, C.A. Marques, and this is my phone number. is my
All
presentation.
right. All right. Thank you, Matthew. So, anyone has any questions about the project? Anything you want to say?
The João here, and Kevin. I call you to talk because it is collaborated project. Hello,
Hi,
Kevin.
thanks.
Present
Hello, hello.
you, my other country friend from India, Goa from Goa.
Yes, hi. Yeah, Goa was also a Portuguese colony, so I'm quite familiar with Portuguese people and the culture here.
Uh, Francisco said, no, no, sorry, was uh, Fones. This project is open to PRs. Yeah, we're gonna open this project to the public in probably today or on the Monday. We're gonna open the project and everyone can contribute to this, but not right now. It's a closed project.
Nice, Kevin. Is now everything out? Is the X connect? Hey, good to see you here, man.
Yeah, I remember Alfonso from Slack. We spoke once over call.
Have so many times. Congrats on the talk, Matheus. Really cool projects and the animations were really pretty. Thank you. Have many job in this project. I I lost 3 days of my sleep, but I really fun with this project. I really happy to to explain for everyone this. I opened this project in today. Today I open to community use. I think about this project is prerequisites to understand the OTP. I think about you make your own or do your Talk project too, but I can share to if you cannot create this to zero do zero. Kevin.
So, folks, I think it is that we over on 11 a.m. on Brazil. Uh, anyone wants to talk more about anything, have questions, or just talking in the general?
Someone presentation here. A little about yourself. Select handle people to to talk about a little about yourself. What is your job? Is your favorite favorite language? What is your elixir level? Someone? Everyone
Yeah,
is shy today.
I think it is it. So, thank you guys. It was a beautiful presentation from everyone and a lot of things to learn. And I excited to study all the things that was said today. So I guess it's it. Thank you for all for you for joining and bye bye.
Bye bye. See you soon. See you
Bye,
soon.
everyone. Have a nice day.
Yeah. And for all the Brazilians, Falou, gente. Bom sábado.
Bye bye.